Picture the recommendation engine behind a short video app like Kuaishou or TikTok. Every time you open the app, the system has to look at your entire history of watches, likes, and follows, blend that with information about millions of candidate videos, and then predict half a dozen different things at once, whether you'll watch to completion, whether you'll like it, whether you'll share it. For years, the way teams improved these systems was to scale up one piece at a time. Make the behavior model bigger. Make the feature interaction module fancier. Add more experts to the multitask head. But this piecemeal approach is hitting a wall, and the paper we're looking at today, UniFormer from Kuaishou, argues for a fundamental shift in how we think about scaling these systems. The motivation comes straight from what we've all watched happen with large language models, or LLMs. There, the lesson was that monolithic scaling of a single transformer architecture beats clever handcrafted modules. Recommendation researchers have been trying to import that lesson, but their attempts have been partial. Methods like rank mixer scale just the feature interaction operator. Methods like HyFormer and MixFormer take a step further by jointly scaling behavior modeling and feature interaction together, but they stay confined to what the authors call the feature space. The task modeling side, the part that handles having many prediction objectives like watch time, likes, and follows, gets left out of the unified scaling story. It's like renovating 2 rooms of a house with a coherent design while the third room still has 1990s wallpaper. So the question UniFormer asks is, can we build one unified transformer-style architecture that scales across behaviors, non-sequential features, and tasks all at once, while still meeting the brutal latency requirements of serving hundreds of millions of users in real time? The challenge has 3 parts. You need efficiency because naive, full self-attention across everything would be far too expensive. You need to prevent what they call preference collapse, where mixing all behavior signals together causes the model to lose distinct short-term versus long-term interests. And you need flexible parameter allocation so capacity can be added wherever it helps most. Here's how UniFormer is structured. Everything starts with tokenization, which means turning raw features into compact vector tokens. They split features into 3 buckets. Sequential behaviors like your recent watches and your long-term compressed interest representation get tokenized element by element. Non-sequential features like user profile or item metadata get grouped semantically. And crucially, they're separated into item-independent groups, which only depend on the user and request, and item-dependent groups, which involve the candidate video. Then task-related features get their own tokens, 1 per prediction objective. This semantic grouping isn't cosmetic. It's the foundation that lets them later compute the user-side representation just once per request and reuse it across all the candidate videos being ranked, which is a massive serving win. Now comes the heart of the model, what they call the Unified Interaction Block. It has 2 stacked modules. The Feature Space Interaction Module, or FIM, handles interactions between sequential and non-sequential features. The Task Space Interaction Module, or TIM, sits on top and handles how those rich feature representations relate to the various tasks. The clever trick that makes this efficient is borrowed from a design principle in OneRec v2 called the lazy decoder. Instead of doing expensive intra-sequence self-attention over the whole behavior history, sequential features only appear as keys and values in cross-attention layers, never as queries. Think of behavior sequences as a library that gets consulted, not a debate club where every book argues with every other book. The non-sequential and task tokens are the readers who query that library. Inside FIM, they make a deliberate choice that addresses the preference collapse problem. Rather than concatenating short-term, long-term, and search-based behavior sequences and running one shared cross-attention over the mess, they run separate cross-attention paths for each sequence type, each with its own dedicated feed-forward network. The intuition is that short-term browsing and long-term lifelong interests live in genuinely different latent spaces, and forcing them through a shared network causes the model to collapse onto whichever signal dominates. After extracting these distinct views, they fuse them with either a global learned coefficient or a per-user personalized coefficient that depends on things like activity level, which is especially valuable for cold start users where short-term signal is sparse. Then, a self-attention layer mixes everything together for higher-order feature interaction, followed by what they call multi-view FFNs, separate feed-forward networks for sequential outputs, non-sequential outputs, and task outputs, so capacity can be allocated independently to each. Tim then mirrors this structure, but for tasks, using cross-attention so each task can adaptively attend to whichever high-order features matter for it, analogous to a mixture of expert-style task representation. On the engineering side, two optimizations make this practical at Kuaishou's scale. For training, they use variable length flash attention to avoid padding waste in heterogeneous behavior sequences, plus BF16 mixed precision. For inference, the semantic tokenization plus an attention mask that blocks user queries from attending to item keys means the user-side computation happens exactly once per request, then gets reused across all 500 or 1,000 candidates being ranked. That's where the request-level acceleration comes from. The results are meaningful in industrial terms. Offline on Kuaishou's dataset, UniFormer beats the strongest cross-module co-scaling baseline, MixFormer, by about 0.1% in GAUC across 4 tasks. And remember, the authors note that 0.05% GAUC is considered highly significant at this scale. A larger version with nearly 1 billion parameters pushes gains further, and scaling curves show clean improvements as they grow the multi-view FFNs, which is exactly the kind of clean scaling law that's been hard to achieve in recommendation. Online A/B tests on the main Kuaishou app and Kuaishou Lite delivered roughly a 0.1 to 0.26% lift in app stay time and 0.7 to 1.1% lift in watch time. Ablations confirm the design choices, removing multi-sequence cross-attention Hertz interaction tasks like likes the most, and replacing the multi-view FFNs with shared ones causes the biggest drop overall. That said, there are real limitations worth naming. The reported online lifts, while real, are modest compared to the parameter increase, going from around 115 million dense parameters to nearly 1 billion for a sub-% gain in watch time raises questions about return on infrastructure investment. The scaling curves they show only go up to about 1 billion parameters, so we don't really know whether this architecture would keep scaling like an LLM does into the tens of billions. The lazy design that gives them efficiency also means sequential elements never directly interact with each other, which could limit modeling of fine-grained behavioral patterns like sequences of related actions. And the approach depends heavily on having clean semantic feature grouping, which is a non-trivial engineering exercise that's easier at a company with mature feature platforms than for newer teams. Now let's walk through some questions you might have after hearing all of this. First, why does the lazy cross-attention design, where sequential tokens only show up as keys and values, never as queries, actually work well enough? The intuition is that in ranking, you're not really trying to understand the internal structure of a behavior sequence the way you'd parse a sentence. You're trying to extract a summary of user interest conditioned on your current context, which is the non-sequential and task tokens. Those queries pull the right information out of the behavior library, and full self-attention over the sequence would mostly add cost without adding signal. The empirical results back this up, and you save enormous compute. Second, what's actually causing preference collapse, and why does running separate cross-attention paths for each sequence type fix it? When you concatenate short-term and long-term behavior tokens and apply one shared attention, the softmax tends to concentrate weight on whichever sequence has stronger or more numerous signals, often the recent short-term activity, and the model effectively learns to ignore the others. By giving each sequence its own cross-attention path and its own feed-forward network, You guarantee that each behavior source gets its own representation extracted in its own latent space before fusion, so the long-term signal can't be drowned out during attention. Third, how does the semantic tokenization actually translate into faster serving? Concretely, when a user request comes in, the system has to rank maybe 1,000 candidate videos. Without decoupling, you'd recompute the user's behavior representation 1,000 times, once per candidate. UniFormer's tokenization explicitly separates tokens that depend only on the user and request from tokens that depend on the candidate item, and the attention masks ensure user-side tokens never attend to item-side tokens. So the user-side forward pass runs exactly once, and only the much smaller item-side computation gets repeated per candidate. At 1,000 candidates per request and Kuaishou's traffic, that's the difference between a feasible deployment and a non-starter. Bringing this back to large-scale recommendation systems generally, there are a few concrete takeaways worth carrying forward. The user item decoupling pattern enabled by semantic tokenization is broadly applicable. Any ranking system that scores many candidates per request can save dramatic compute by structuring its model so user-side state is computed once and reused, and this paper gives a clean template for how to do that even inside a transformer architecture. The multi-sequence cross-attention idea is also directly portable. Most production systems already maintain multiple behavior sequences for short-term, long-term, and search-based interests, and treating each with its own attention path, plus a personalized fusion coefficient, is a relatively low-risk change that could improve cold start and lifecycle robustness. More broadly, the model-centric scaling thesis matters for any team thinking about where to invest. Instead of asking which module to make bigger next, the question becomes how to architect a unified backbone where capacity can flow to whichever component the data demands, with multi-view FFNs being a simple but effective mechanism for that. For retrieval as well as ranking, the lazy cross-attention pattern offers a path to scaling sequence modeling without the quadratic cost that usually kills these ideas in production. The honest caveat is that you need mature feature infrastructure and serving optimizations like flash attention and BF16 to make this pay off. But if you have them, this paper is a credible blueprint for the next generation of ranking architectures.